So good afternoon, everybody. So my name is Minhan. I'm a software engineer on the GK networking team.
And I'm Rohit, also software engineer on GK networking.
So today we're here to share our experience running and supporting Kubernetes at Google. So networking is hard, and Kubernetes networking can get even harder. So at Google, we have levels of support for customer issues. And we are the last line of defense. So when the customer issues get to us, they better be tricky. And this talk, we don't want to make it into a lecture or training sessions, although some of the slides come from our internal training sessions. So we first pick a few fun cases, and then we're gonna talk about what are the lessons learned and what are the best practices we think we should share with the community. So first case, it's a black hole. So let me explain the setup a little bit. So it's a service with 3 backends, and the deployments has three replicates, and this service is actually a UDP service with a port 53. It looks very suspiciously similar to a kubedns. So a client pod comes in. So the client pod, in this case, is a green one. It sends a request to the service cluster IP. And we're going to use Matthew McConaughey from Interstellar to represent the network packet. So the packet gets to the service cluster IP, and the service is supposed to load balance the request. The service picks one backend and then delivers the packet to the backend. And in this case, Matthew is happy. And let's say the service backend changes for whatever reason, rescaling or no disruptions or upgrades, whatnot. So one of the pods is gone. And the cross represent the deployment is irrelevant here, so it's removed. So the green pod, again, it sends another network packet. It goes to the service, and this time a black hole shows up. And it swallows all the requests, and no backend gets it. And Matthew is sad in this case. So this actually happens like a while back, but and this is consistently, like the green pod's request will get swallowed consistently. So to explain what happened, we need to talk about some of the background knowledge. So first is contract. So contract stands for Linux kernel connection tracking. So it basically provides the functionality to remember the network address and the port translations happen inside the kernel. So it's based on the 5 tuples, like protocol, source IP, source port, destination IP, and destination port, and the packet will get reversed. The network address translation will get reversed on the way back, so that the client will not get confused. So on the example on the right, so on top you see the original request is sending from port 1 to service 1, and it got translated to the destination IP got translated to port 99. This happens when the service, request gets to a cluster IP, and the cluster IP load balances it to one of the backend pod. The next background knowledge is NetFilter. NetFilter is a very important Linux component. It stands for Linux Packet Filtering Framework. It gives like hooks to allow users to intercept and manipulate network packets, and it's capable of network filtering, which is used by network policy, and also network address translation or NATing, and port translation, which is used for a kubeproxy to do the service load balancing. And IPtables, EBtables, contract tables, and etc. are all part of the NetFilter framework. So on the right, we have a snippet of the NetFilter processing flow chart. So it's a very complex, but we're only gonna talk about what's relevant here. So in this case, the network packet comes from the network interface, and then it enters the pre-routing hook. It's provided by the NetFilter, and then within the pre-routing hook, it first checks if there is an existing contract entry matches the network packet. If it is, then it will go proceed. If not, then it will first look at, it will pass the packet to the NAT table to see if it matches any of the natting rules, and then take it from there. So let me explain what happened in the black hole case. So first, the packet comes in, and the service picks a backend, and a contract entry is created. In this case, the source, the original destination IP is the cluster IP, and then it got translated to the yellow pods IP. Okay? So the second time, when the request comes in, there's an existing contract entry that matches the packet, and then the black hole shows up because contract entry decided to forward it to stale endpoint, which is the yellow pod, which doesn't exist anymore, causing the black hole. So what we learn from this, so it's when we have contract can only be turned on for all the network traffic. You can turn it on or off for all, but you cannot turn it on for partial traffic. And then we have natting, which we use extensively with kubeproxy to implement the Kubernetes service. And then the nature of UDP, which doesn't guarantee the reliable delivery, and there's no UDP, there's no connections there. So, and then the ephemeral nature of pods, which pods come and go all the time. And then that's a recipe for black hole. So the fix for this is actually happened in kubeproxy. So what we did is that we flush the stale contract entry when the backend changes. We will find the corresponding backend, the corresponding entry, and then we flush it so that the next packet comes in, it will go through the NAT table and then go deliver to the right backend. But this is still a problem because there's a slight gap between like flushing the endpoint, flushing the backend, and the new backend and the backend changes, right? There's always a gap between, so you will get a UDP packet loss basically. And also for UDP in general, it's very tricky because the timeouts, how the kernel decide whether this UDP is timeout or not is just by looking at the source, looking at the whether the packet matches the existing contract entry, and there's a kernel parameter to configure it. But let's say you have a very long timeout, then you are risking the black hole. But if you have a very short timeout, then probably the request and response cannot make the round trip. Then it's always tricky for UDP. Well, we have another case for a black hole. So this is a typical pod networking setup on a VM. So you have a big giant gray rectangle to represent a VM, and then inside this VM, we have multiple network namespaces. So you have a root namespace which contains the ETH0 that connects the VM to the network fabric, and then the CBR0, which is the container bridge, is also in this root namespace. And each pod gets a separate network namespace. That's the default mechanism for the pod isolation. So to connect the network namespace, pod 1 uses a network, each pod gets a virtual network interface pair, and then it's basically like a network cable. It's one end is in the pod's network namespace, the other end is hooked up on to the network bridge within the root namespace. That's a very typical network setup on a Kubernetes node. And in this case, network traffic can flow between pod 1 and pod 2, and basically between the pods on the same node, but no traffic can come in or go out from the VM. Basically, nothing can reach the pods on the VM, and the pods cannot reach out. It was as if there's a black hole in between that swallows all the traffic. So this actually happens, and then and then multiple customer issues get into our pipeline. And then finally, there's an internal customer, which is another Google team. And usually we don't have access to the customer's node. And this time we had an internal customer. Then we asked them, hey, give us permissions to log onto a VM and take a look at what happened. And then we debugged the hell out of it. And then what we found is quite tricky. So memory pressure happened on the VM. And then the kernel started killing processes. So then, in this case, the network D, which is a very important Linux component that is basically in charge of the networking stack, got killed because it got a very bad score. And then there's a particular network D bug in that kernel, which resets a kernel parameter on restart. The kernel parameter decides whether ETH0 on the VM is allowed to forward packet or not. In this case, it reset to 0. That means the ETH0 are not allowed to forward packet. So that's why nobody can get in, or nobody can get no traffic can get in, or no traffic can get out. So what we learned in this case, so you have to dig deeper. So sometimes, before we get to the root cause, we always suggest the customer to say, oh, hey, don't try to overload your VM, and then you might get into this problem. And then when you get into this problem, restart. Because restart, we're gonna refresh the kernel configs. But like in this case, it's actually a kernel bug. And then fortunately at Google, we have a whole team to support the host OS, which we call the container optimized operating system, which runs for GKE nodes. And then the team gets the bug and they fix the bug. So this will not happen once again. And then secondly is the kernel configs really matters. Kubernetes depends a lot of Kubernetes features depends on the kernel itself.
Okay, so we talked a little bit about black holes. Now we'll get into a wormhole. So the setup for this one, on the right in the yellow, we have a daemon set called A, and that daemon set exposes a host port 443. And in the blue, we have a service type load balancer, which is also exposing port 443, and that's kind of fronting a deployment of 2 replicas, and we can call that B. So how this kind of looks, we have our load balancer, and we have 3 nodes, and the daemon set obviously exists on all 3 nodes, and the deployment exists on the left and right ones. And we can represent our packet again with our astronaut, and he hits the load balancer VIP at port 443 to talk to B. And he gets routed to this node. This is a particularly unlucky node, you'll see in a second, because it contains both A and B. So what happened was the request was intended for B, but it got sent to A. And that makes him very sad. So before we can get into why this happened, let's do a little refresher on IPtables. So IPtables is how we implement service routing and quote-unquote load balancing in Kubernetes. IPtables rules are configured by both kubeproxy and kubelet. Kubelet takes care of one specific case, which is the host port case. Kubeproxy takes care of everything else. And like Minhan mentioned before, IPtables works on top of NetFilter. And so on the right is a really, really simplified view of how it kind of works. We'll go into a much more detailed view of how it actually works in Kubernetes in a little bit. But as you can see, we register at hooks, could be like a pre-routing or output, and we install a bunch of chains. In reality, we have a couple layers of nesting of chains, and eventually we get to the actual rules, which, it can be a bunch of things, but in the simplest case, it can be if your destination IP is this or your port is this, then do something, right? And so now we can look at what happened. So in this case, A was created. This is the daemon set. And as I mentioned before, kubelet programs the IPtables rules for the host port. And so what happened was it programmed one rule in a chain, and it basically said, if the destination port's 443, then DNAT to A's IP. Now, B is created. This is the deployment, and therefore kubeproxy programs the IPtables rules. And because it's a separate exposure type, as in service is different from the host port, we actually have to create a new chain for that. It's not on the same chain. Therefore, we have another chain here, and the rule in a really simplistic view says if the source IP is a load balancer VIP, then DNAT to B's IP. And so what happens is this created a wormhole, right? And so any packet coming in that had a destination of port 443, which in this case was both, it always got DNATed to A's IP, regardless of what the intended destination was. And so we kind of like to coin this as a wormhole. And so some things we learned here. IPtables is really tricky, and there's two reasons why. The first is you need to make sure that rules are as explicit as possible. As you saw, that first rule, which basically swallowed up all traffic on port 443, was not explicit. It was really wide. And we should aim for having rules that are really narrow and cover a very, very small set of use cases. And the second thing is that rules should be precedence agnostic. It shouldn't really matter where in the order your rule is executed. It should be this. It shouldn't matter, right? But in this case, it did. If we had moved that first rule to be the second one, we would have never seen this issue. Okay, and so now we're going to get into some best practices, stuff that we've learned, debugging customer issues. And I know debugging networking, at least for me, it can be really hard to just get started. It can be really daunting. But what we like to do is kind of identify sources of truth. And these sources of truth kind of give you a definitive view of how the system is going to act and what the state of the system is in at any point in time. And so one of the first sources of truth is IPtables. This is kind of how the IPtables dump would look if you went on a node and just called IPtables save. This is, for at least me when I first saw it, really daunting, but if you kind of break it down step by step, it makes sense. So let's do that. So this first chain here is called kube services, and we can see that any packet that's destined for 10.0.16.10, which is just a cluster VIP, cluster IP VIP, sorry, jumps to this chain called kube service in the green. And this is kind of representative of a service, right? So we have our cluster IP there. Okay, and so now we have two more chains here. The kube SEP, which just stands for endpoint, service endpoint. And this is just kind of this is why we say quote unquote load balancing, because we basically use probability to distribute between the endpoints. And so you can see there are two endpoints here, and that's how we have represented it here at the bottom, two endpoints. And then for each of those endpoints, we can see that a DNAT occurs to a specific IP, and that's a pod IP. And that's represented by those right there. Okay, next source of truth, contract. Contract is a really good way to see the state of the system in a dynamic way. Whereas IPtables is kind of static. It doesn't show you what's going on at any given time. Contract does. And so we have kind of two examples here. The first is a really simple, just kind of pod-to-pod communication case. As you can see, the stuff in the blue tells you that it's an entry for traffic from one pod to the other, and then the red is the way coming back. And then the second case is a little more interesting. Actually, you can tell by looking at the source IP, that would be a load balancer IP. And the destination port in the blue is a very common node port. So this kind of gives you a clue that this is an entry for a node port type service.
Okay. All right, so generally, when we look at a custom issue, we first determine whether this is a control plane problem or data plane problem. So that you can tell by like the symptoms and what are the problems you show up. So when it's a like control plane problem, generally speaking, go to the logs first. Logs, events, and we'll see what happened. And then take it from there. For data plane, it's a little bit tricky because the stack is a little bit deeper. So first from the user space, you have the application coming from the user space, and then it enters the kernel space, and then finally get out to the network fabric. So there's many places to look at. So in this example, we're gonna show you like a sample like troubleshooting methodology or process that we do. In this case, the customer is like complaining the DNS queries are timing out. So first things first, we need to figure out how's the traffic flow, what's the data plane looks like. So first, the traffic comes out from the client pod. The client pod sends the request, goes to the CBR0, and traverse the IPtables, and out of the ETH0 interface to the network fabric. And then magically the network fabric delivers the packet to the destination node. And then the destination node route the packet to the DNS server pod. In this case, the request doesn't end here because kubedns only serves cluster internal DNS queries. When it finds the queries it cannot serve, it will forward to upstream DNS servers. In this case, the DNS server pod process it and decide, okay, I'm gonna forward it. And then the traffic will come out and to the CBR0 bridge, out to the network fabric, and go to the upstream DNS. So DNS query is timing out. So like, what do we look at? So first thing first, did it actually send out the request, right? This can be told by the application logs. To tell it definitely, you need to use TCP dump to see if actually the request comes out from the interface. So just keep in mind that TCP dump works at the interface level. So you have to attach to an interface. It depends on how the traffic flows and whether the traffic gets natted or not. You will see the packet as it arrives on the interface. So in this case, you can dump it on the ETH0 inside the pod namespace, or outside. If you do TCP dump in the root namespace, then you need to find the correct VF pair of the pod, and then dump on that interface. And then you can tell whether there's DNS request actually coming out from the pod. And then you can also dump on the CBR0 bridge and see if the CBR0 bridge is actually routing, taking the traffic and routing it correctly. And finally, you can dump on any interfaces and see if the IPtables are actually processing the request correctly, whether it's forwarding the traffic to a correct backend. And when the packet goes on to the network fabric, then it's the typical stuff to look at on your network fabric, where you need to look at routes, if you are using an overlay, whether the overlay is functioning correctly, your firewalls, and all the other stuff. So, and then on the destination node, check on the ETH0 to see if the destination node actually accepts the traffic. And then finally in the DNS pod and see if the requests are actually coming from the client pod. And the server logs can tell you whether the server is actually receiving it and then how it's getting processed. If you want more verbosity, you can use strace to attach to the server pod's the process ID and then see what syscalls it is making. And then similarly to check if the outgoing requests, the forwarded requests are actually heading to, in this case, 8.8.8.8, and then etc. So eventually you can see, okay, what breaks in the whole data plane. So that basically concludes our talk. So networking is hard, but like with some patience and more background knowledge, Kubernetes networking is not magic anymore. All right, so. Any questions?
It's over there.
What about the IPBS one?
I can talk about that.
Yeah, so
You said, what about IPVS? Yeah, so good that you mentioned that, actually. IPVS, for anyone who doesn't know, it's just another form of load balancing in the kernel. It's actually more adept to load balancing than IPtables is. It's actually beta in Kubernetes right now. The plan is to go GA with it in the next release, which is 1.11. But to your question, IPVS is still built on top of NetFilter. Just the way it kind of uses those hooks is a little different. Like IPtables, we do DNAT and pre-routing, whereas in IPVS they do DNAT and the input. And so stuff like that varies, but for the most part, the underlying like stuff is the same. So. Yeah, I mean, it's a different technology, and it's one that all of us on the team have to get onboarded to. And so we definitely expect problems, but it's good that the underlying technologies are the same, and we're familiar with that, so, yeah. There.
Do you use the basic tools, so do you have tools that get you all the Kubernetes kernel data, so you have an easier job using speed up or strace to enrich that?
Yeah, we are happy.
Oh, doesn't work?
Well, time's up.
Yeah, doesn't work the mic.
You can come down.
Yeah.
Your mic does work.
Oh, it works now? Okay. So the question is, like, any other tools that we recommend to? I see.
Do you have custom tools? Because
So
certainly basic networking tools work, but you get a
so there are more monitoring and logging like support on GKE, but generally speaking, we can't touch the user's VM, so that gives us a lot of a barrier. So sometimes we have to ask the users to give us, to execute something for us, and then to give us more clue what's happening. And we are also thinking of kind of like a debug toolkit or something that can be deployed as a privileged pod on any node and then have a better debugging. So, but that has a lot of dependency. So first the node has to be functioning, and things like that. So,
But for now, we use that. Whatever you saw is what we use.
Here you've covered a bunch of known issues and wormholes. The problem with using Kubernetes in production often is these wormholes show up out of nowhere. And yes, you can use these methods of debugging, figuring out what went wrong. But do you have like a recommendation of some sort of active check framework or passive check framework to put in place so at least I can get the pods out of that host and then isolate the issue and deal with it later?
so the question is that wormholes are common, right? That's what you experience. It depends on the setup, I think. It depends on your kube proxy implementation and all your network provider. So if those are compatible, usually these happens when they are not compatible. They say, okay, it's two components are programming IPtables and they don't know each other, they collide. That happens, right? So it really depends on your network setup, and whoever manages the setup needs to make sure that these are compatible, right? I think that's the right answer, where it needs to be fully tested out in all the corner cases, like hairpin traffics or other like natted traffic or no port. So basically, there's a variety of a networking test suite exists on the Kubernetes repo where it has to pass, right? And then yeah, that's basically my answers. Yeah, like not end user. I would say whoever manages the cluster, right? Yeah. Yeah, yeah. Any, okay. Yeah, we're yeah, we had a lot of ideas like but the thing is that troubleshooting every issue is very different, and then hopefully because Kubernetes is still very young compared to a lot of other projects, it's still like 3 years old, believe it or not. It's still having so much adoption. So there are like if at Google, if you are a very mature project, engineers should not get any like customer issues at all, right? So right now we are still getting the fact that we're still getting it means that it's not perfect. So we are also learning and exploring. Like you said, it's a very common problem where you have many pages of nodes and things like that. Yeah, that can get very daunting, but we don't. Mm-hmm. When you ask about security, the answer is always defense in depth, right? So it provides you a certain level of security. You say network policy, can you rely on it? Yeah, maybe, but at a certain level. And then you are talking about container level security. Then you probably want like gvisor, right, where you have real a sandbox around your container. Yeah. Yeah, yeah. Ask the Calico guys. They'll tell you it works. Yeah, our talk is mostly about like what doesn't work well. So, all right. Any other questions? Or we can always chat offline. Right. All right. Thank you.